All right, let's dive right into this hands-on explainer. Today, you aren't just a student reading about math, you are stepping into the role of a universal mathematical architect. We're going to get our hands dirty and physically build the absolute foundations of geometry together.
So to kick things off, here's a kind of crazy question. What in the world connects Pac-Man to a reclining chair? You might not realize it yet, but understanding the hidden geometry around us reveals some truly amazing connections. By the end of our time together, you'll see exactly how your favorite retro video game character and your favorite spot to just chill and relax are totally bound by the exact same rules of geometry.
To uncover these secrets, we're going to build everything from absolute scratch today. And we're using just 4 basic tools in your geometry toolkit. We'll start with tiny points, stretch them out into lines, crash those lines together to create angles, and finally, we'll wield our ultimate measuring device, the protractor.
Okay, Section 1, the blueprint basics. We're looking at points, lines, segments, and rays.
Every great blueprint has to start with a single mark, right? Imagine taking a super sharp pencil and stamping a tiny, invisibly thin dot right there on your desk. That exact precise location is your point. In geometry, we name these points using capital letters. So if you draw 3 dots, you literally read them as point Z, point P, and point T. It's the core building block of our entire universe.
Now, what's really interesting here is the stark difference between a line segment and a ray. Think about folding a piece of paper and unfolding it. You get that clear, crisp crease. That crease is securely anchored between 2 fixed ends, which makes it a line segment. It's the absolute shortest route from point A to point B. But a ray? Well, a ray is a lot wilder. It has a starting point, sure, but then it just shoots off indefinitely in one direction. Forever.
And you can clearly see how we take a physical tool, place it firmly on our paper, and actually build this stuff. By laying down a ruler right between point A and point B, we can physicalize that shortest distance, bringing that line segment to life right on the page.
Moving right along to Section 2, the birth of an angle. Let's talk about the vertex, arms, and naming.
So what happens when those straight rays finally collide on your paper? Something entirely new is born. Picture bringing 2 rays together until their endpoints physically touch. That exact joining point where they crash into each other, that's your vertex. And once they're connected there, those 2 rays officially become the arms of your brand new angle.
Now, here is an absolutely crucial rule. When you're naming your creation, the vertex must be protected right in the center. If your arms have points P and M and your vertex is point O, you definitely don't call it PMO. No way. You lock that vertex right in the middle, balancing the arms on either side, and you call it angle POM.
Section 3, the Protractor Masterclass. Let's do some step-by-step measurement.
All right, grab your protractor because we are entering the action zone. I want you to literally imagine sliding your protractor onto the page right now. Step 1. Place that little center target right smack on the vertex. Step 2. Physically rotate the protractor so the bottom straight edge, the 0-degree baseline, lines up perfectly flat with one of the arms. Step 3. Run your eyes up the second arm and see exactly where it crosses the curved numbers on the outer edge. Boom. That number right there is your exact degree measure.
Let's put this to the test and build our skills. Imagine visualizing and locking in these exact targets. Try drawing specific measurements like 40 degrees, 75 degrees, or all the way up to 134 degrees. By carefully aligning that baseline, you are the architect. You are forcing that angle to be exactly the size you demand.
On to Section 4, the Angle Detective. It is time for some visual cheat codes.
Because hey, sometimes you just don't have a protractor handy, right? It all starts with one absolutely magic number, 90 degrees. This number represents our first major structural benchmark.
If you look at an angle and the arms form a perfect L, you have found yourself a right angle. It's exactly 90 degrees. Think of the crisp corner of a heavy textbook, or even the corner of your phone screen. It is rigid, perfect, and straight up and down.
Now, take that 90 degrees, double it, and what do you get? Our next crucial measurement, 180 degrees.
At 180 degrees, you've essentially pushed the angle open so far that the 2 arms flatten out completely. It just becomes a perfectly flat, straight line. And yup, you guessed it, we call that a straight angle.
But what happens when the angle isn't perfectly 90 or perfectly 180? Well, notice how the sharp, biting crocodile mouth of an acute angle completely contrasts with the relaxed, open seat of an obtuse angle. An acute angle is anywhere between 0 and 90 degrees. It's much sharper and more closed than an L. But if it pushes past 90 degrees, opening up wider than an L but not quite completely flat, it becomes an obtuse angle. Think of leaning way back in a really comfortable reclining chair.
Okay, now for the ultimate boss level of angles. The trickiest one of the whole shebang, the reflex angle. This is an angle that has bent all the way backward, past a flat 180 degrees. Remember our Pac-Man question from the very beginning? Imagine Pac-Man's open mouth. If the acute angle is that small space inside his mouth where he eats the dots, the reflex angle is the huge curved space all the way around the outside of his head.
So, you've got the toolkit, the naming rules, the protractor action steps, and the visual cheat codes. Now, I have a living room geometry challenge for you. Scan the room you're in right this second. Can you spot a slightly open door to represent your sharp acute angle? Or maybe a window corner to serve as your perfect right angle? Prove you're a true geometry architect. You see, geometry isn't just trapped in textbooks. It's the invisible framework holding up the room you're sitting in right now. So tell me, once you start seeing the math hiding in plain sight, what other hidden architecture are you going to discover holding your world together?